Good day everyone. Today we will be discussing how to determine natural frequency of multi-degree freedom systems using matrix method as part of the course Me22088 Vibration and Noise Control. My name is Dr. C. Sennamare. I am Associate Professor in the Department of Mechanical Engineering at SVC. Welcome back. In this segment, we are going to revisit the concept of eigenvalue problem, specifically in the context of solving systems of second order linear homogeneous differential equations, often encountered when analyzing vibrating systems. Our goal is to solve the equation that is mx double dot plus kx equal to 0. Here M represents mass matrix, K represents stiffness matrix of our system, and X is the displacement vector as a function of time t. To find the solution, we are going to make a crucial assumption about the form of x of t. We will assume that each component of the displacement vector, let's call it x I suffix of t, can be expressed as the product of a constant vector xi and a scalar function of time t of t. In other words, x of t equal to x of I t of t, where I ranges from 1 to n, representing the degrees of freedom of our system. For example, degree of freedom is 2 means I will be 1, 2. While t of t encapsulates the time dependent behavior common to all components. Now let's substitute this assumed solution back into our original equation. When we are substituting here back into our original equation, we will get that x double dot will be retransformed into x t of t, where it is, since still it is double dot only, that constant vector x doesn't depend on time, we can pull it out of the second derivative with respect to time. Hence this gives us m x double dot of t plus kx t of t equal to 0. Now we can rewrite this same equation by considering the ith component of this vector equation, that is 1 to n. This will look like the equation as it is presented here. We can factor out the time dependent term outside, that is t by t we can factor out, and its second derivative t of double dot of t. This is second derivative, this is the first one. So because from this equation, if it is rearranged, we will get the factor out equation, which is rearranged in the form of summation of k stiffness into x divided by summation of mass into x of I, where I is going to be ranging from 1 to n. Notice that the left hand side of this equation is a function of time only, while the right hand side is a ratio of constants. Since mass m of ij, k of ij, xj are all constants, for this equality to hold for all time t and for all I2 is varying from 1 to n, both sides must be equal to the same constant value. We typically denote this constant as omega. Therefore, the crucial step here sets the stage for formulating the eigenvalue problem. The next slide, we will explore how this leads to finding natural frequencies and mode shapes of our system. In the previous slide, we arrived at a crucial point where we recognized that t double dot of t must be equal to a negative constant, which we are denoting it as omega square. This is because the left hand side of the equation involving only the function of time, it is independent of the index I, while the right hand side is involving the system properties, the constant vector x, which is independent of the time t. The only way for this equality to hold is if both sides are equal to the same constant is, that is, we can use omega square for this constant, where omega square is a positive value as it directly relates to the frequency of oscillation. So we now have a simple second order linear ordinary differential equation for T of t. This is a well-known equation that describes simple harmonic motion. The general solution to this equation is given as C1 cos omega t plus pi, where C1 is the amplitude of the oscillation and pi is the phase angle. That is, these two constants C1 and pi are determined by the initial conditions of the systems. What's truly remarkable about this solution is its implication for the motion of our entire system. Since we assume that each coordinate xi is given by capital Xi, and we have now found that T of t is a sinusoidal function with frequency omega and phase angle pi. It means that all coordinates of the system will perform a harmonic motion with the same frequency and the same phase angle. They will oscillate together in sync, although possibly with different amplitudes determined by the components of the vector x. This frequency omega is known as the natural frequency of the system, and it is inherent property determined by mass and stiffness characteristics of the system. In the last slide, we add the equation such a way that it is in the form of summation of k of ij minus omega square m of ij into x of I equal to 0. This is from the first slide. This is the eigenvalue program. Otherwise, we can say it is a eigenvalue problem. Bringing all terms to one side, we are getting this. We can further combine these summations, this set of n linear homogeneous equation, because n linear means if the variable is going to be displacement is going to be more than 1, it is equal to n number of displacements, means n variables will be come into picture. So it will give us n linear homogeneous equations. So ladies and gentlemen, here this equation is the eigenvalue problem. Once again, I am reiterating it. Here k is the stiffness matrix, m is the mass matrix, omega square is the eigenvalue what we are looking for, and x is the eigenvector which represents the mode shapes. Very important, this is the eigenvector. For this system of homogeneous equations to have a non-trivial solution, what is the meaning of non-trivial solution? It is this x is not just a zero vector. The determinant, then what is 0 here? The determinant of this coefficient matrix must be 0. This x is not 0. Okay, so this determinant will be equal to 0. This equation is known as the characteristic equation or the eigen equation. Solving this equation for omega square will give us the eigen values of the system. Remember that omega square is nothing but square of the natural frequency. So taking square root will give us the natural frequencies of vibrations. Each eigenvalue that we find when substituted back into the eigenvalue problem will allow us to solve for the corresponding eigenvector. Very important step, I am telling this. What we have to do, find out the eigenvector. After finding the omega square eigenvalue, we have to substitute in the eigenvalue problem to calculate the eigenvector. This in turn represents, this eigenvector is in turn represents mode shape associated with that particular natural frequency. This mode shape tells us the relative amplitudes of motion of the different parts of the system when it vibrate at the specific natural frequency. This one we already seen in the previous video, that how the 3 degree of freedom system behave and how to draw the mode shape using the each and every natural frequency. Now let's look at a specific example of how the matrix method can be used. In this case, our objective is to determine the natural frequency of the given spring mass system. Please kindly note that this is our second problem, calculating the natural frequency using matrix method. We have a system consisting of three masses connected by springs. The masses are 2m and the second mass is also 2m, third mass is m, and the spring constants are given as 2k, k and k. We have defined the displacement of these masses as x1, x2, x3 respectively. Let we use the Newton's second law to calculate the natural frequency. The first step is we have to derive the equation of motion for each mass. These equations describe how the forces acting on each mass when it is subjected to force and result in its acceleration. As you can see, the equations involve the masses, spring constants and the displacement of the masses. For example, for the first mass, the acceleration is nothing but accelerating force is nothing but mass into acceleration, that is mx double dot, the displacement first one. Since the mass is 2m, we have to substitute as a mass in terms of 2m plus the stiffness force acting only with respect to the mass is going to be 2k. So 2k into velocity x dot plus k into, this is the second stiffness force where the displacement is going to be with respect to both mass 1 and mass 2. So we have to write x1 minus x2 equal to 0. Whenever a stiffness is going to be in between the two displacement, then the difference of displacement will be utilized. So for the stiffness force acting at k, it will be, for mass 2 means it is x2 minus x1, for mass 3 means it is x2 minus x3. So with using this stiffness forces, when we are applying the Newton's law for all these three masses, we are getting this following three simultaneous equation. Now what we have to do means we convert this into mass matrix and stiffness matrix. To apply the matrix method, we first need to represent the mass properties of the system in this mass matrix form. For this system, the mass matrix is a 3 by 3 diagonal matrix with the masses along the diagonal, that is 2m, 2m, m. Remaining everywhere it is 0. Since it is 0, there is no direct coupling of inertia items between the masses in this representation. The determinant of this matrix M is an important property. In this case, the determinant is calculated as 4m cube. Next, we will calculate the inverse of the mass matrix, that is M inverse. The inverse is then given by 1 by determinant, that is 4m cube, and using the transpose and the inverse calculation, which is very much crucial in determining the natural frequency, we can calculate, and we are having that the inverse matrix here, it is 2m square and 4m square the values. So it is the next step we will see from the next slide. So there we are going to be use the stiffness matrices and finding its roots of the equation which will correspond to calculate the natural frequencies. Following the determination of the mass matrix and its inverse, the next crucial step in finding the natural frequency involves considering the stiffness matrix of the system. While stiffness matrix itself isn't explicitly shown on this slide, we know that the system matrix C, often denoted as C, is related to the inverse of the mass matrix and the stiffness matrix K by the equation C equal to M inverse dot K. Hence, we will substitute the stiffness matrix here. So in this, you can see that a stiffness matrix has been multiplied with the mass matrix, and this is going to be the 1 by 2m is the outcome of the inverse matrix. Next, we are multiplying this mass matrix with the stiffness matrix. We got this equation. To find the natural frequencies, we utilize the concept of eigenvalue. We assume omega square equal to lambda, where omega represents natural frequency. Natural frequency can then be found by solving the characteristic equation, which is given by the determinant, that is lambda into I minus C, which is equal to 0, where I is the identity matrix, C we already know it is system matrix. So now we are substituting lambda into identity matrix minus C. C is this matrix. So lambda minus 3k by 2m. Just you are substituting here. Similarly, lambda minus k by 2m. Then it is 0. Okay. So similarly, along the stiffness matrix only it will come, because along the diagonal only it will come, because it is identity matrix. Identity matrix means 1, 1, 1 along the diagonal. So we will get this matrix. From this we are going to find the equation, just matrix multiplication. Determinant of this matrix we are finding out, it is lambda cube minus 3.5 lambda square k by m plus 3.25 lambda k square by m square minus 0.5 k cube by m cube equal to 0. Using the characteristic equation, we are going to obtain the roots of this characteristic cubic equation. Then the roots correspond to squares of the natural frequency of the system. As you can see here, the slide provides the value of this roots as lambda 1 is 0.2 k by m. Then we can substitute omega square equal to lambda. Then we will get omega 1 equal to 0.44 root of k by m. In the similar fashion, we can able to get lambda 2 value, we can substitute, and we will get natural frequency omega 2. Similarly, we can substitute lambda 3 equal to 2 of k by m in the same equation, omega square equal to lambda. We will get omega cube equal to 1.414 root of k by m radians per second. So for this mass system, we are getting that lambda 1, lambda 2, lambda 3 as this value, and substituting omega square equal to lambda, we are getting the natural frequency. In some kind of problems, stiffness and mass matrix will be given in terms of value, like k equal to 10 Newton per meter, mass equal to 10 kg. Like that, if it is given, we can substitute these values and we can able to calculate the natural frequencies in terms of discrete values. These three natural frequencies represents inherent frequency of the spring mass system, which will tend to oscillate when it is disturbed. Understanding these frequencies is crucial in designing systems to avoid resonance, which can lead to catastrophic failures. This example demonstrates how the matrix method can be systematically applied to determine natural frequencies of a multi-degree of freedom systems.